पहले भी मैं design rate limiter. In a network system, a rate limiter is used to control. In this chapter, you are asked me to design the rate of the traffic sent by a client or service. In the HTTP world, a rate limiter limits the number of client requests allowed to be sent over a specified period. If the API request count exceeds the threshold defined by the rate limiter, all the excess calls are blocked. Here are a few examples. A user can write no more than 2 posts per second. You can create a maximum of 10 accounts per day from the same IP address. You can claim rewards no more than 5 times per week from the same device. In this chapter, you are asked to design a rate limiter. Before starting the design, we first look at the benefits of using an API rate limiter. Prevent resource starvation caused by denial of service attack. Almost all APIs published by large tech companies enforce some form of rate limiting. Twitter limits number of tweets to 300 per 3 hours. Google Docs API have the following default limit: 300 per user per 60 seconds for read requests. A rate limiter prevents DOS attacks, either intentional by blocking the excess calls. Reduce cost. Limiting excess requests mean fewer servers and allocating more resources to high priority APIs. Rate limiting is extremely important for companies that use third party APIs. For example, you are charged on a per call basis for the following external APIs: check credit, make a payment, retrieve health records. Limiting the number of calls is essential to reduce costs. Prevent servers from being overloaded. To reduce server load, a rate limiter is used to filter out excess requests caused by bots and users' misbehavior. Understand the problem and establish design scope. Rate limiting can be implemented using different algorithms, each with its pros and cons. The interactions between an interviewer and a candidate helps to clarify the type of rate limiters we are trying to build. What kind of rate limiter are we going to design? Is it a client-side rate limiter or server-side API rate limiter? We focus on the server-side API rate limiter. Does the rate limiter throttle API requests based on IP or the user ID or other properties? The rate limiter should be flexible enough to support different sets of throttle rules. What is the scale of system? Is it built for a startup or a big company with a large user base? The system must be able to handle a large number of requests. Will the system work in distributed environment? Yes. Is the rate limiter a separate service or should it be implemented in the application code? It is a design decision up to you. Do we need to inform users who are throttled? Here is the summary of the requirements for the system. Accurately limit excessive requests. The rate limiter should not slow down HTTP response time. Use as little memory as possible. Distributed. The rate limiter can be shared across multiple servers or processes. Show clear exceptions to users when their requests are throttled. If there are any problems with the rate limiter, it does not affect the entire system. Let us keep things simple and use a basic client and server model for communication. We can implement a rate limiter at higher either the client or server side. Client side implementation. Generally speaking, client is an unreliable place to enforce rate limiting because client requests can easily be forced by malicious actors. Moreover, we might not have control over the client implementation. Shows the rate limiter that is placed on the server side. Besides the client and server-side implementations, there is an alternative way. Instead of putting a rate limiter at the API server, we create a rate limiter middleware which throttles request to your APIs as shown. Let us use an example to illustrate how rate limiting works in this design. Assume our API allows 2 requests per second. A client sends 3 requests to the server within a second. The first 2 requests are routed to API servers. However, the rate limiter middleware throttles the third request and returns a HTTP status code 429, indicates that user has sent too many requests. Cloud microservices have become wildly popular, and rate limiting is usually implemented within a component called API gateway. API gateway is a fully managed service that supports rate limiting, SSL determination, authentication, IP whitelisting, servicing static content. For now, we only need to know that API gateway is a middleware that supports rate limiting. While designing rate limiter, an important question to ask ourselves is, where should the rate limiter be implemented? On the server side or in a gateway? There is no absolute answer. It depends on your company's current technology stack, such as programming language, cache service. Make sure your current programming language is efficient to implement rate limiting on the server side. Identify the rate limiting algorithm that fits your business needs. When you implement everything on the server side, you have full control of the algorithm. However, your choice might be limited if you use third party gateways. If you have already used microservice architecture and included an API gateway in the design to perform authentication, IP whitelisting, you may add a rate limiter to the API gateway. Building your own rate limiting service takes time. If you do not have enough engineering resources to implement a rate limiter, a commercial API gateway is a better option. Rate limiting can be implemented using different algorithms, and each of them has distinct pros and cons. Even though this chapter does not focus on algos, understanding them at the high level helps to choose the right algo or combination of algos to fit our use case. Here is a list of popular algos: token bucket, leaking bucket, fixed window counter, sliding window log, and sliding window counter. Token bucket algo is widely used for rate limiting. काय हा आपल्या चॅनल ही चॅनल आहे की आपलं हं. उगं वाजत बसायचं हा आणि घ्या म्युसिक मला कशाला घ्यायला ते तसले मोठे ते असे टोपेसारखे आणि ती फिरतोय बी असा कॅमेरा इकडे तिकडे फिरतोय आवाज आता तू जर बोलला का मीटिंग मोठी असते बोलला का तिकडे लगेच खास करून फोकस करतो क्लॅरिटी असली असते की A token bucket is a container that has predefined capacity. Tokens are put in the bucket at preset rates periodically. Once the bucket is full, no more tokens are added. As shown, the token bucket capacity is 4. The refiller puts 2 tokens into the bucket every second. Once the bucket is full, extra tokens will overflow. Each request consumes 1 token. When a request arrives, we check if there are enough tokens in the bucket. If there are enough tokens, we take 1 token out for each request and the request goes through. If there are not enough tokens, the request is dropped. Illustrates how token consumption refill rate limiting logic works. In this example, the token bucket size is 4 and the refill rate is 4 per 1 minute. And the refill rate is 4 per 1 minute. Enough tokens? No. Start with 4. The token bucket algorithm takes 2 parameters: bucket size and refill rate. Number of tokens put into the bucket every second. The maximum number of tokens allowed in the bucket. How many buckets do we need? This varies and it depends on the rate limiting rules. It is usually necessary to have different buckets for different API endpoints. If a user is allowed to make one post per second, add 150 friends per day, and like 5 posts per second, 3 buckets are required for each user. If we need to throttle request based on IP address, each IP address requires the bucket. If the system allows a maximum of 10,000 requests per second, it makes sense to have a global bucket shared by all requests. The algorithm is easy to implement, memory efficient. Token bucket allows a burst of traffic for short periods. A request can go through as long as there are token lefts. Two parameters in the algorithm are bucket size and token refill rate. However, it might be challenging to tune them properly. The leaking bucket algorithm मला समजलं नाही algorithm का करते नेमकं. If the if there are enough tokens, we take 1 token out for each request and the request goes through. If they are not enough again the request. बोला. हा. हम्म. प्रिफिक्स. हा. हा. असं आहे का? हम्म. हम्म. मग आता तुझी टाइम कॉम्प्लेक्सिटी ऑर्डर ऑफ एन स्क्वेअर आहे. सोल्युशन करेक्ट आहे का? सोल्युशन करेक्ट आपले टाइम जास्त गेले आणि स्पेस कॉम्प्लेक्सिटी ऑर्डर ऑफ एन आहे. नाही नाही तुझ्या तू जे आता साईज किती घ्यायले. तुझा ॲरे जर का तुझं इनपुट जर का एन साईजचा असेल तर तुझं तू ॲरे एक बनवायलास ना एक्स्ट्रा ॲरे बनवायलास N+1 साईजचा. N+1 म्हणजे ऑर्डर ऑफ एनच झालं. बरोबर आहे. बरोबर बोलू का मी? हा मग हा हे ह्याला ह्याला म्हणजे एंगेजिंग कन्व्हर्सेशन. समोरच्या माणसाला प्रश्न विचारला बरोबर आहे का नाही? हा. मग इंटरव्ह्यू मध्ये पण असंच करायचं. असं बोलायचं मी बरोबर बोललो का नाही सांगा म्हणायचं. तुम्हाला जर चुकीचं वाटलं त्यांना लोक हा करत पडलेलं असते. हा मग आता तुझ्याकडे स्पेस अगोदरच ऑर्डर ऑफ एन स्पेस वापरायला आहेस. मग तू अजून एक जर का हॅश मॅप वापरलास तर तुझं काय वाईट व्हायलंय का? नाही. मग आता कारण हॅश मॅप पण ऑर्डर ऑफ एन साईजच घेते. हॅशटॅग म्हणजे काय? हॅशटॅग म्हणजे काय नसते फक्त की आणि व्हॅल्यू एक टेबल असते. टेबलमध्ये फक्त हॅश टेबल फक्त दोन कॉलम असते त्याच्यामध्ये. एक कॉलम एका कॉलम मध्ये की असते एकामध्ये व्हॅल्यू असते. डिक्शनरी डिक्शनरी सर. समजलं का? मग आता तुला लॉंगेस्ट सब ॲरे विथ गिव्हन सम काढायचे आणि ते इनपुट काय आहे तुला फक्त एक ॲरे मिळायला आणि के मिळायला. के म्हणजे त्याचे तुझं टार्गेट आहे ते. बरोबर आहे. मग आता 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 तुला लॉंगेस्ट सबॅरे विथ गिव्हन सम काढायचे. मग तू आणि तू प्रिफिक्स अरे अगोदर कॅल्क्युलेट केलायस. प्रिफिक्स कॅल्क्युलेट केलायस मग तुला आता प्रिफिक्स हा हा आता म्हणजे आता तुझे जे नंबर जे तुझे नंबर्स आहेत त्यांचे त्यांची रेंज किती आहे. अरे जे नंबर्स आहेत त्यांचं डोमेन किती आहे. म्हणजे जे झिरो हा कन्स्टंट 0 to पॉझिटिव्ह आहेत का निगेटिव्ह पण अलाउड आहेत कसं आहे. टी म्हणजे नंबर ऑफ टेस्ट केसेस किती टेस्ट केसेस आहेत. हा पुढे. हा. हा बरोबर आहे पुढे. हम्म. हा म्हणजे पॉझिटिव्ह नंबर्स आहेत फक्त. बरोबर आहे. नाही नाही ॲरे साईज ॲरे साईज हा. हा ॲरे साईज 10⁵. हम्म. हम्म. हा मग आता बघा. हम्म. हम्म. हा म्हणजे आणि इंटिजरची रेंज कुठून कुठपर्यंत असते जवळपास -10⁹ पासून 10⁹ पर्यंत असते. आणि ही नंबर सुद्धा एक जर का तुझ्या नंबर जर का फक्त पॉझिटिव्ह असते तर आणि त्यांची जर का तू प्रिफिक्सम कॅल्क्युलेट केला असतास तर ती प्रिफिक्सम तुझी सॉर्टेड आली असती. बरोबर आहे. सुरुवातीला काय नंबर नसतं एक. हा एक. हा. हा. हम्म. 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 म्हणजे परंतु तू आता इन नंबर्स निगेटिव्ह नंबर्स असल्यामुळे तुझी सम पुढे भविष्यात कमी पण होऊ शकते. बरोबर आहे. हम्म. मग आता आता हा हा पाठव. आणि आता बघ अजून बघ. मग आता हॅश मॅप मध्ये तू काय सेव्ह करायचं माहितीये का. हॅश मॅप बनवायचा इंटिजर टू इंटिजरचा. नाही सॉरी इंटिजर टू वेक्टर ऑफ इंटिजरचा म्हणजे तुझी की राहणारी इंटिजर आणि मग हे स्ट्रायव्हरचा व्हिडिओ बघ हॅशमॅपचा व्हिडिओ स्ट्रायव्हरचा त्याचं स्ट्रायव्हरचा सर्च कर एस टी एल हॅश मॅपचं एखादं बाईक 5-10 मिनिटाचा व्हिडिओ बघ लगेच समजून एस टी एल हॅश हां हां काय नाही एस टी एल हॅश मॅप एस टी एल हॅश मॅप काय बघायचे हां नाही नाही हां ते सगळं त्याने इंटरनली हँडल करते तुला गरज नाही त्याची हम्म. हां हां कळालं
Heap memory, on heap memory, off heap memory, memory management, partitioning, coalescing.
थांब थांब तुला तुला एक लिंक पाठवलं काय आता व्हॉट्सअपवर पण आले की स्क्रीन शेअरिंग हां व्हॉट्सअपवर स्क्रीन शेअरिंग आले काय फक्त कॉल लावल्यावर नंतर येते बटन
Video calls on the
व्हिडिओ कॉल हो डिस्कॉर्ड थांब मी तुला व्हिडिओ कॉल का इथं ऑप्शन काय मेक कॉल्स अच्छा विंडोजवर ॲप लागते विंडोज ब्राउझरमधून करता येत नाही
video call होत नाही browser होते रे.
तुला लिंक पाठवला बघ मॅपच्या ट्युटोरियलची काय नाही 10 मिनिटाचं आहे लई मोठं नाही आणि हे पाठव ती तुला कोड पाठव व्हॉट्सअपवर ब्राउझरमध्ये ओपन कर की व्हॉट्सअप तुला काय मग उघड उघड ॲप उघड आणि कोड कॉपी पेस्ट करून पाठव मला आणि ही व्हिडिओ बघता तुला डोक्यात काय आयडिया आली तर ती इम्प्लिमेंट कर नाहीतर निवांत बस जेवण नंतर जेवण करून ये नंतर बघू आपण ठेवू का हां कोण का बरं?
कसलं hash map on heap memory.
नावच ऐकायला भारी वाटतं तर. तू 2-4 प्रश्न सोडवलास का नाही तुमचं काय चुत्या पाहिजे हॅलो झक मारायला
म्हणजे माशा माशा हो माशा आहेत तिथं.
बघ बघ माझ्या मित्राला माहिती आहे झक म्हणजे मासे असतात म्हणून माशा नाही मासे असतात मासे
माशा तेच की.
हां.
Plural.
कुठं काय निघाली का नाही गाडी अजून हां कुठं म्हणजे कुठून कुठं पाठवलं गेले तुम्हाला याला तर जयराम दिले
Use this.
जयराम दिले मित्राच्या वडिलाचं नाव जयराम आहे त्याला वाटलं त्याला चिडवावं काय आमच्या ग्रामदेवतेचं नाव आहे जयराम
काय म्हणतोस?
हो. मित्राला शॉक बसला
Token
म्हणतो माझ्या माझ्या माझे वडील देव आहेत का म्हणते
in the bucket as was received towards the So when the bucket is full, no more tokens are added.
हा चालतं मग ते दिलो का नाही त्याला का खायला वेळेला
Token bucket capacity is 4 to the full plus. Token takes the bucket every second, so when the bucket is full, extra token more. So each request consumes one token. When a request arises, they check if there are no tokens in the bucket. If there you take one token
हा
for each request and request.
मी काय नाही युट्यूबवर लाईव्ह स्ट्रीम करायला
If there are enough tokens, the request is dropped.
काय युट्यूबवर व्हिडिओ टाकायला नाचायचा
Token consumption is different rate. Logic works if the request tokens less for the request. No request.
जेवण खाणं झालं
When request multiple
जायच्या करायच्या आधी
start with token for every be challenging to tune them properly, leaking the bucket algorithm, the leaking bucket algorithm is similar to the
गुरुजी काय करायला गुरुजी
accept that request and process that.
गुरुजी काय करायला
Is usually implemented in the first and first out.
कशाची
That when the request arrives, the system checks if the queue is full. If it is not full, the request is added to the queue. Or if the request is dropped, request is fully from the queue and process that request.
आणि ते पाईप लावलं का नाही अजून लावलं का नाही
Request algorithm takes following to parameter the hit size of the request given.
हम्म. हम्म. स्टँड भेटले का नाही नसेल भेटायला ऑनलाईन मागवलं स्टँड हम्म. 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 माप घेतले म्हणजे हां 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 तुझं होय म्हणजे तुम्ही आता जाऊन फिरून येणार नंतर बसणार का असं आहे. हम्म. किती जाता बोला किती जातं खालची वरची डावीकडली उजवीकडली चालतं ठेवू का नाही नाही ठेवतो लाईव्ह स्ट्रीमवर सगळे घरचे कॉल सुरू आहेत माझे काय का नाही
खरंच करलेलास का काय
लाईव्ह स्ट्रीम सुरू आहे की मग काय एंड स्ट्रीम लाईव्ह 21 मिनिट लाईव्ह स्ट्रीम सुरू आहे
बघ का तुला सर्च करू का?
सर्च केल्यावर येईल चॅनलचं नाव सर्च केल्यावर येईल यम दोनाळे म्हणून काय तर नाव यायचं बी नाही वाटायला मला
पब्लिक केलास का?
हा पब्लिक आहे यम दुधनाळे लाईव्ह स्ट्रीम अरे मुड मुडदूस मंगेश नायरे लहू दुधनाळे प्रभाकर दुधनाळे स्वाती दुधनाळे धोंडीराम दुधनाळे अरे हे लहू दुधनाळे काका आहे माझा प्रभाकर दुधनाळे माझा काका आहे
फॅमिली पूर्ण युट्यूबच्या बिझनेस मध्ये बसली काय
लाईव्ह
दूध नाळे आले ना
चॅनलचं नाव काय आहे मला संभवू दे
टायटल काय त्या स्ट्रीमचं
अरे हे दुसरं आहे यम महेश दुधनाळे 9953 महेश दुधनाळे सर्च कर बोलते जाऊ दे मी मला माहित नव्हतं ते ही चॅनल आहे म्हणून.
ही तुझे का
हे दुधाने ती
नाही ना ती पूर्ण ऍड्रेस टाकता मी
कुठं
ऍट महेश दूध नाळे
ऍट
9953
तुला लिंकच पाठवतो सोड इथं कुठे इथे का शेअरची शेअर कसं करायचं हे माहित नाही आपल्याला पार्टिसिपेंट्स मी एकटाच आहे मीच लाईक करतो अरे नाही लाईकचं ऑप्शन नाही अरे हो की ही लिंक आहे वाटतं ही लिंक शेअर केल्यावर येते का
स्टुडिओ
इथे शेअरचं बटन आहे आता सापडलं आता येते काय नाही ही दुसरी लिंक आहे हे आता येते कमेंट कर मला चांगलं वाटतं कमेंट कर
खरंच लायचं
ये
तिथं पाय घातात नाही गेलास ना
लेटेस्ट बघितली आहे की ते मी इथं हसल्यावर 5 सेकंद गेले चॅट मध्ये कर बर इथे का चॅट हे फायर तुला हे सगळं माहिती आहे का नाही हो कोलन तो इमोजी नाव टाईप केलं इमोजी इथे
सगळीकडे तरी
हम्म.
सेमी कॉलन का नुसतं कॉलन
नुसतं करू
तसं-
डेस्कटॉपवर आहे वाटतं होती. हा आता आपण पुढचा अल्गोरिदम बघू मित्रांनो. खाली वाकू नका जास्त. दुसरं काहीतरी दिसेल. The leaking bucket algorithm is similar to the token bucket, except that requests are processed at a fixed rate. Mute केलंस का? मला ऐकू कसं काय ना. It is usually implemented with a FIFO queue. The algorithm works as follows. When a request arrives, the system checks if the queue is full. If it is not full, the request is added to the queue. Otherwise, the request is dropped. Requests request is pulled from the queue and processed at regular interval. Algorithm takes following two parameters. Bucket size equals the queue size. The queue holds the request to be processed at a fixed rate. It defines how many requests can be processed at a fixed rate. Uses key buckets for rate limiting. Memory efficient given the limited queue size. Requests are processed at a fixed rate. Therefore, it is suitable for use cases that a stable outflow rate is needed. A burst of traffic fills up the queue with old requests, and if they are not processed in time, recent requests will be rate limited. Fixed window counter algorithm. The algorithm divides the timeline into a fixed size time window and assign a counter for each window. Each request increments the counter by one. Once the counter reaches that predefined threshold, the new requests are dropped until a new time window starts. Let us use a concrete example to see how it works. The time unit is 1 second and the system allows a maximum of 3 requests per second. If more than 3 requests are received, extra requests are dropped as shown in figure. A major problem with this algorithm is that the burst of traffic at the edges of time windows could cause more requests than allowed quota to go through. Consider the following case. The system allows a maximum of 5 requests per minute, and the available quota resets at the human-friendly round minute. As seen, there are 5 requests between 2 and 2:1, and 5 more requests between 2:1 and 2:2. For the 1 minute window between 2 and 2:1, 10 requests go through. That is twice as many as allowed requests. Memory efficient. Easy to understand. Resetting available quota at the end of unit time fits fits certain use cases. The fixed window counter algorithm has a major issue. It allows more requests to go through at the edges of the window. The sliding window log algorithm fixes the issue. It works as follows. The algorithm keeps track of request timestamps. Timestamp data is usually kept in cache, such as sorted sets of Redis. If विजया फॅमिली ग्रुपवर लिंक शेअर करतो कोणतरी येईल बघायला कॉपी लिंक ॲड्रेस फॅमिली ग्रुप. The algorithm keeps track of request timestamps. The timestamp data is usually kept in cache. When a new request comes in, remove all the outdated timestamps. Add timestamp of the new request to the log. If the log size is the same or lower than the allowed count, a request is accepted. We explain the algorithm with an example as revealed in figure. Allow 2 requests per minute. In this example, the rate limiter allows 2 requests per minute. Usually, Linux timestamps are stored in the log. However, human readable representation of time is used in our example. The log is empty when a new request arrives at 1:1, so the request is allowed. A new request arrives at 1:30, the timestamp 1:30 is inserted into the log. After the insertion, the log size is 2, not larger than the allowed count. When a new request arrives at 1:50, the timestamp is inserted into the log. After the insertion, the log size is 3, larger than the allowed size 2. Therefore, this request is rejected even though the timestamp remains in the log. A new request arrives at 1:40. Requests in the range हॅलो. हा. आता मी आता मी ग्रुपवर एक लिंक पाठवला बघ. व्हॉट्सअपवर. त्या लिंकवर त्या लिंकवर क्लिक कर. युट्यूब उघडते. युट्यूब कर बरं. उघडलं का? हम्म. फोन ठेवायची गरज नाही. करता येते अशी. हॅलो. कुठं आहेस? असं आहे का? तर काय नाही. व्हॉट्सअपवर एक लिंक पाठवलं होतं. ती लिंक उघडलं का? माझा व्हिडिओ दिसतोय. ठेवू का? The sliding window counter algorithm is a hybrid approach that combines the fixed window counter and sliding window log. The algorithm can be implemented by two different approaches. We will explain one implementation in this section and provide reference for the other implementation at the end of the section. Assume the rate limiter allows a maximum of 7 requests per minute, and there are 5 requests in the previous minute and 3 in the current minute. For a new request that arrives at a 30% position in the current minute, the number of requests in the rolling window is calculated within the following formula. Okay. Since the rate limiter allows a maximum of 7 requests per minute, the current request can go through. However, the limit will be reached after receiving one more request. Due to space limitation, we will not discuss the other implementation here. Interested readers should refer to the reference material. This algorithm is not perfect, it has pros and cons. अरे हिच्यात तू काय इमोजी पाठवायलास काय? हा. हा. मला वाटलं घरच्या पाठवलेत काय की. एक एक दोन किती नाही तू एकटाच आहेस. पार्टिसिपेंट मध्ये तू एकटा दिसायस. मी जातो मुतायला. दिसतंय का मुतायला गेल्यावर? दिसतंय वाटतं जातो मुतायला उघडलेलं दिसतंय. कौन है? The basic idea of rate limiting algorithms is simple. At the high level, we need a counter to keep track of how many requests. कौन है रे? The basic where shall we store counters? Using the database is not a good idea due to slowness of disk access. In-memory cache is chosen because it is fast and supports time-based expiration strategy. Redis is popular option to implement rate limiting. It is an in-memory store that offers two commands: increment and expire. The client sends a request to the rate limiting middleware. Rate limiting middleware fetches the counter from the corresponding bucket in Redis and checks if the time limit is reached or not. If the limit is reached, the request is rejected. If the limit is not reached, the request is sent to API servers. Meanwhile, the system increments the counter and saves it back to Redis. The high-level design in figure does not answer the following questions. How are rate limiting rules created? Where are the rules stored? In this section, we will first answer the questions regarding rate limiting rules and then go over the strategies to handle rate limited requests. Finally, we will discuss Lyft open source their rate limiting component. We will peek inside of the component and look at some examples of rate limiting rules. Domain messaging, descriptors message type, value marketing, rate limiting unit day request per unit 5. In the above example, the system is configured to allow a maximum of 5 marketing messages per day. Here is another example. नमस्कार मनोज उद्नाळे, कसे आहात? भेटली का नाही तुटी? हा, तुटी भेटली का नाही? किती रुपयाला भेटली तुटी आहे? In case the request is rate limited, API returns a HTTP response code 429. Depending on the use cases, we may enqueue the rate limited request to be processed later. How does a client know whether it is being throttled? And how does a client know the number of allowed remaining requests before being throttled? The answer lies in HTTP request response headers. The rate limiting returns the following HTTP headers to client. X rate limit remaining, the remaining number of allowed requests within the window. Rate limit, it indicates how many calls the client can make per time window. Rate limit retry after, the number of seconds to wait until you can make a request again without being throttled. When a user had sent too many requests, a 429 too many request error and a X rate limit retry after header are returned to the client. Figure presents a detailed design of the system. Rules are stored on the disk. Workers frequently pull rules from the disk and store them in the cache. When a client sends a request to the server, the request is sent to the rate limit middleware first. Rate limiter middleware loads rules from the cache. It fetches counters and last request timestamp from Redis cache. Based on the response, the rate limiter decides if the request is not rate limited, it is forwarded to API servers. If the request is rate limited, the rate limiter returns 429 too many requests error to the client. In the meantime, the request is either dropped or forwarded to the queue. Building a rate limiter that works in a single server environment is not difficult. However, scaling the system to support multiple servers and concurrent threads is a different story. There are two challenges: race condition synchronization issue. As discussed earlier, rate limiter works as follows at the high level. Read the counter value from Redis. Check if counter plus 1 exceeds the threshold. If not, increment the counter value by 1. Race condition can happen in a highly concurrent environment. Assume the counter value in Redis is 3. If two requests concurrently read the counter value before either of them writes the value back, each will increment the counter by 1 and write it back without checking the other thread. Both requests believe they have the correct counter, however, the correct counter value should be 5. Locks are the most obvious solution for solving race condition. However, locks will significantly slow down the system. Two strategies are commonly used to solve the problem. Lua script and sorted sets data structure in Redis. For readers interested in these strategies, refer to the corresponding reference material. Synchronization is another important factor to consider in a distributed environment. To support millions of users, one rate limited server might not be enough to handle the traffic. When multiple rate limited servers are used, synchronization is required. For example, on the left side of the figure, client sends the requests. Performance optimization is a common topic in system design interviews. We will cover two areas to improve. First, multi data center setup is crucial for a rate limiter because latency is high for users located far away from the data center. Most cloud service providers build many edge server locations around the world. Cloudflare has 194 geographically distributed edge servers. Traffic is automatically routed to the closest edge server to reduce latency. Second, synchronize data with an eventual consistency model. If you are unclear about the eventual consistency model, refer to consistency section in chapter 6, design a key value store. After a rate limiter is put in place, it is important to gather analytics data to check whether the rate limiter is effective. The rate limiting algorithm is effective. The rate limiting rules are effective. If rate limiting rules are too strict, many valid requests are dropped. In this case, we want to relax the rule a little bit. In another example, we notice our rate limiter becomes ineffective when there is a sudden increase in traffic like flash sales. We may replace the algorithm to support burst traffic. Token bucket is a good fit here. We discussed different algorithms of rate limiting and their pros and cons. Token bucket, leaking bucket, fixed window, sliding window log, sliding window counter. Then we discussed the system architecture, rate limiter in a distributed environment, performance optimization, and monitoring. Similar to any system design interview questions, there are additional talking points you can mention if time allows. Rate limiting at different levels. In this chapter, we only talked about rate limiting at the application level. It is possible to apply rate limiting at other layers. You can apply rate limiting by IP addresses using IP tables. The open system interconnection model has 7 layers. Avoid being rate limited. Design your client with best practices. Use client cache to avoid making frequent API calls. Understand the limit and do not send too many requests in short time frame. Include code to catch exceptions or errors to your client so your client can gracefully recover from exceptions. स्वस्त भेटली ॲमेझ बरं झालं भया स्वस्तात भेटली बरं काही तोटी नाहीतर ॲमेझॉनवर 250 म्हणाल तर आता फक्त स्टँड बघावं लागणार आहे स्टँड आता स्टँड राहिलंय तुला बसवता येते का डिझाईन आता पुढचा चॅप्टर वाचू आपण डिझाईन consistent hashing. To achieve horizontal scaling, it is important to distribute requests efficiently and evenly across servers. Consistent hashing is commonly used technique to achieve this goal. But let us take an in-depth look at the problem. If you have n cache servers, a common way to balance the load is to use the following hash method. Let us use an example to illustrate how it works. As shown in table 5, to fetch the server where a key is stored, we perform modular operation. For instance, this one, that one. This approach works well when the size of the server pool is fixed and the data distribution is even. However, problems arise when new servers are added or existing servers are removed. If server 1 goes offline, the size of server pool becomes 3. Using some hash function, we get the hash value for a key, but applying modular operation gives us different server indexes because the number of servers is reduced by 1. We get the results as shown in table 5 by applying hash number 3. हॅश स्पेस अँड हॅश स्ट्रिंग मी जरा हे अगोदर वाचलेलं मी स्किप मारतो पुढे जातो जरा बरं का तुम्हाला प्रॉब्लेम असला तर बघा नाहीतर उठून जावा डिझाईन अ की व्हॅल्यू स्टोअर हे महत्वाचं आहे हे मी एक क्वेश्चन सॉल्व्ह केलो पण एवढ्या मोठ्या स्केलवर कधी केलं नव्हतं A key value store, also referred to as key value database, is a non-relational database. In this chapter, we are asked to design a key value store that supports the following operations: put, get, delete. There is no perfect design. Each design achieves a specific balance regarding the trade-offs of the read, write, and memory usage. Another trade-off has to be made was between consistency and availability. We design a key value store that comprises of the following characteristics. The size of the key value pair is small. The ability to store big data. See, developing a key value store that resides in a single server is easy. An intuitive approach is to store key value pairs in a hash table, which keeps everything in memory. Even though memory access is fast, fitting everything in memory may be impossible due to the space constraint. Two optimizations can be done to fit more data in a single server. Data compression. Even with these optimizations, a single server can reach its capacity very quickly. A distributed key value store is required to support big data. A distributed key value store is also called a distributable hash table, which distributes key value pairs across many servers. Cap theorem. In this section, we will discuss the following core components and techniques used to build a key value store: data partition, data replication, consistency, inconsistency resolution, handling failures, system architecture diagram, write path, read path. For large applications, it is infeasible to fit the complete data set in a single server. The simplest way to accomplish this is to split the data into smaller partitions and store them in multiple servers. There are two challenges while partitioning the data. Consistent hashing, discussed in chapter 5, is a great technique to solve these problems. Let us revisit how consistent hashing works at a high level. Next, the key is hashed onto the same ring and it is stored on the first server encountered while moving in the clockwise direction. For instance, key 0 is stored in S1 using this logic. Servers could be added and removed automatically depending on the load. Data replication, okay. Consistency, okay. Strong consistency, weak consistency, eventual consistencies. Weak inconsistency resolution, versioning. Replication gives high availability but causes inconsistencies among replicas. Versioning and vector locks are used to solve inconsistency problems. Versioning means treating each data modification as a new immutable version of data. Before we talk about versioning, let us use an example to explain how inconsistency happens. As shown in figure 6, both replica nodes have the same value. Let us call this value the original value server 1, server 2. As with any large scale system, failures are not only inevitable but common. Handling failure scenarios is very important. In a distributed system, it is insufficient to believe that a server is down because another server said so. Usually, it requires at least two independent sources of information to mark a server down. All-to-all multi-class casting is a straightforward solution. However, this is inefficient when there are many servers in the system. A better solution is to use decentralized failure detection methods like gossip protocol. Each node maintains a node membership list which contains the members' IDs and heartbeat counter. Each node periodically increments its heartbeat counter. Each node periodically sends heartbeat to a set of random nodes, which in turn propagate to another set of nodes. Once node receives heartbeats, membership list is updated to the latest info. If the heartbeat has not increased for more than predefined periods, the member is considered as offline. Handling temporary failures. After failures have been detected through the gossip protocol, the system needs to deploy certain mechanisms to ensure availability. A technique called sloppy quorum is used to improve availability. Instead of enforcing the quorum requirement, the system chooses the first W healthy servers for writes and first R healthy servers for reads on the hash ring. If a server is unavailable due to network or server failures, another server will process the requests temporarily. This process is called hinted handoff. Since S2 is unavailable in figure 6, when S2 is back online, okay. हे पुस्तक लय भारी आहे बरं का. तुम्ही सगळ्यांनी वाचा. मस्त मजा येते. Data center outage could happen due to power outage, network outage, natural disaster. To build a system capable of handling data center outage, it is important to replicate data across multiple data centers. Even if a data center is completely offline, users can still access data through the other data centers. Now that we have discussed different architectural technical considerations in designing a key value store, we can shift our focus on the architectural diagram. Master diagram, बरं का, लय भारी diagram आहे. Clients communicate with the key value store using simple APIs, get value key, put key. A coordinator is a node that acts as a proxy between the client and the key value store. Nodes are distributed on a ring using consistent hashing. The system is completely decentralized, so adding and removing nodes can be automatic. Data is replicated at multiple nodes. There is no single point of failure as every node has the same set of responsibilities. As the design is decentralized, each node performs many tasks. Write path explains what happens after a write request is directed to a specific node. Please note that the proposed design for write read paths are primarily based on the architecture of Cassandra. Cassandra. Thandagaramanda. हाय का चाललंय माऊ काय नाही हा लय दिवसानं आलो हा हरीला सोडलो का नाही गाडीचा नंबर बिंबर काय बघितलो का नाही? सोबत कोणता मास्तर गेला हरीच्या? आजचा मुक्काम कुठे आहे मग त्याचा? हा, ऐका आमचे प्रवचन मस्त आहेत का? जर प्रवचन मस्त असले तर कमेंट मध्ये लिहा मस्त आहे म्हणून. MAST मस्त लिहा, MAST मस्त. तुमच्यासाठी काय पण. हा. After a read request is directed to specific node, it first checks if data is in the memory cache. If so, the data is returned to the client as shown in figure 620. The Bloom filter is used to figure out which SS tables might contain the key. SS tables returns the result of dataset. The result of the dataset is returned to the client. Goal ability to store big data. Use consistent hashing to spread the load across servers. High availability reads. Data replication, multi data center setup. High availability writes. Versioning and conflict resolution with vector clocks. Dataset partition, consistent hashing. Incremental scalability, consistent hashing. Heterogeneity, consistent hashing. Tunable consistency, quorum consensus. Handling temporary failures, sloppy quorum and hinted handoff, handling permanent failures, Merkle trees, handling data center outage, cross data center replication, design a unique ID generator in distributed systems. एकदम मस्त आहे. ऑल द बेस्ट फॉर युअर वर्क. कुठलं वर्क आणि कुठलं काय तुम्ही सोडून गेलो काय की? इन दिस चॅप्टर नमस्कार नमस्कार सगळ्यांचं इथं स्वागत आहे. In this chapter, you are asked to design a unique ID generator in the distributed systems. Your first thought might be to use primary key with the auto increment attribute in a traditional database. However, auto increment does not work in a distributed environment because a single database server is not large enough and generating unique IDs across multiple databases with minimal delay is challenging. Here are a few examples of unique IDs. Asking clarification questions is the first step to tackle any system design interview question. Here is an example of a candidate interviewer interaction. What are the characteristics of unique IDs? IDs must be unique and sortable. For each new record, does ID increment by one? The ID increments by time, but not necessarily only increments by one. IDs created in the evening are larger. Bye bye. बाय बाय. एक इमोजी इमोजी पाठव, एक इमोजी. बाय बायची इमोजी पाठव, हात पाठव, एक हात. हात पाठीव, हात हात. ऐकू यायलंय का? असं टाटा करायचा, हात पाठीव एक की चॅटमध्ये. मला तुझं बोललेलं ऐकू येत नाही. समजलं का नाही? डू आयडीज ओनली कंटेन न्यूमेरिकल व्हॅल्यूज? Yes, that is correct. What is the ID's length requirement? ID should fit into 64 bits. What is the scale of the system? The system should be able to generate 10,000 IDs per second. IDs must be unique. IDs are numerical values only. IDs fit into 64 bit. IDs are ordered by date. Ability to generate over 10,000 unique IDs per second. Multiple options can be used to generate unique IDs in distributed systems. The options we considered are multi-master replication, UUID, ticket server, tickets, Twitter snowflake approach. Hey Sonia, हाय करला काय माणसावाला सगळे हाय कर.
हाय हाय हाय. अरे गाईस कोण आहे?
गाईज नाही घरच्या इथं.
घरच्या टीम सोबत बोलतोस का?
इथे सुधार आहे. टीम्स नाही, युट्यूब लाईव्ह स्ट्रीम करून आपलं साजूक असते.
बघायचं नाही मी.
हा, लखनगावचं गाबडाई तोंडाची जरा खाली घेऊ तोंड.
बसतो. सर तुमच्या चॅनलचं नाव सांग.
अरे लिंक पाठवू का तुला?
लिंक पाठवा सर.
डायरेक्ट लिंक पाठवतो आपण. लाईक कर लाईक कर लाईक कर.
चॅनल वर आहे की दिल टाका दिल.
एक नंबर एक नंबर आलं. हा यायले की यायले काहीतरी लिहून पाठव लिहून पाठव. तुला लिहायला शिकवलंय का नाही बरं मास्तरांनी? हा हा. लव यू लव यू. दोघ जण कोण बघायला ते मला समजणं झालंय. एक तू आहेत वाटतं आणि एक मावशी आहे वाटतं.
All the best for your work.
माझं बघून ती इन्स्पायर झाली होती, ती बी वाचत बसले माझं बघून. टिकीट
कॅमेरा
सर्व
चांगला वापर रे.
हा
कॅमेरा चांगला वापर रे.
तू म्हणलास म्हणून आता आज मागितो कोड्याचा कॅमेरा मागितो आज मी. Ticket servers are another interesting way to generate unique IDs. Flickr developed ticket servers to generate distributed primary keys. It is worth mentioning how the system works. The idea is to use a centralized auto increment feature. Approaches mentioned above give us some ideas about how different ID generation systems work. However, none of them meet our specific requirements. Thus, we need another approach. Twitter's unique ID generation system called Snowflake is inspiring and can satisfy our requirements. Divide and conquer is our friend. Instead of generating an ID directly, we divide an ID into different sections. Screen bit, timestamp, data center, machine, sequence number, design deep dive. Okay, okay. In this chapter, we discussed different approaches to design a unique ID generator, multi-master replication, UUID, Twitter ticket server, and Twitter Snowflake like unique ID generator. We settle on Snowflake as it supports all our use cases and is scalable in a distributed environment. If there is extra time at the end of the interview, here are a few additional talking points. Clock synchronization. In our design, कोण आहे रे कोण आहे मला हार्ट पाठवले कोण आहे in we assume ID generation servers have the same clock. These assumptions might not be true when a server is running on multiple cores. The same challenge exists the same challenge exists in multi-machine scenarios. Solutions to clock synchronization are out of the scope of this book. However, it is important to understand the problem exists. Network time protocol is the most popular solution to this problem. Section length tuning. Fewer sequence numbers but more timestamp bits are effective for low concurrency and long-term applications. Since an ID generator is a mission critical system, it must be highly available. अयो लई पाठ दुखायले बाबा. एक तास झाला बंद करू का? बाय गाईज एक तास झाला जातो आता शेतावर जातो पाणी दिले मला शेतात